because I do think that this is going to be a game changer for PCB design, right? All of a sudden, well, not all of a sudden, our PCB designers today and for many years have been challenged with, us consumers wanting it faster, it lighter, more functionality in smaller spaces. And ultimately, we're hitting this crunch time in printed circuit board design, where with the 75 micron or 3 mil line in space, you just can't route out the devices that you need in the space that you have. And so you're going to multiple lamination cycles, multiple levels of stacked or staggered microvias, all increasing time, increasing cost, decreasing reliability. And that's the world that we live in with subtractive etch. All of a sudden, this designer has the ability to use, say, 25 micron or 1 mil line in space. It changes the way that you look at designs.
That's my guest, Tara Dunn, next on Reliability Matters.
Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Konrad.
Tara Dunn is a seasoned professional with more than 20 years in the electronics industry, exclusively focused on the PCB sector. Her experience spans roles from manufacturing to sales and marketing. Tara was the founder of Omni PCB, a technical manufacturer's representative for the printed circuit board industry, which specializes in quick-turn projects, PCB design, high-density interconnects, RF microwave PCBs, and more. Tara is also the vice president of marketing and business development for Veritech, which develops and licenses advanced manufacturing processes and the key chemistries that enable them for a variety of electronic products, including very high-density printed circuit boards, semiconductor packaging, RF and millimeter wave passive components. Tara writes a regular column for PCB007.com and is a regular contributor with Altium. Tara also co-publishes PCBadvisor.com. And perhaps most interesting, she was one of the founders of Geek-a-Palooza. We'll get into that and much more in our conversation with Tara Dunn. Tara Dunn, thank you for being my guest today on Reliability Matters. I really appreciate you being here.
Thanks for having me. I'm looking forward to the conversation.
Yes, yeah, as am I. So I got into this industry a long time ago, as my friend and colleague Doug Pauls would say, when mammoths roamed the earth. I think I've heard him say that 400 or 500 times maybe. Back in the mid-'80s, the first time I saw a flex circuit, I just was not overly impressed with the technology. It just seemed to be a connector, a flexible connector, some piece of what looked like mylar or whatever they're made out of. I'm sure you'll correct me later. But it was basically just used to connect two rigid boards together, or a print head, or something along those lines. Now I see boards, flexible circuits that are really circuits. They actually have components soldered to them, and they're much more sophisticated than they used to be. So for the sake of my audience and me in particular, walk me down the road of flexible circuits. What's the difference between a flex circuit and a rigid flex? What evolutionary paths did that technology take from the earlier days of flex circuits to where we are today?
Happy to do that. It's funny that you mentioned that, because I had a similar experience when I started in the industry. First, I come to the industry very much by accident. I didn't know what a flexible circuit, or barely what a printed circuit board was, when I started in the industry years ago, but have been in the industry for many years, most of it focused on flex and rigid flex. So I have picked up a thing or two, but when I was first learning, I had, like I said, a similar experience. It looked like a ribbon cable, maybe connecting two different areas on a circuit board together, single-sided, double-sided, very low component count type designs. And then I kind of worked through a progression of technology as I learned as well, going to multi-layer flex, going to rigid flex, going to bookbinder flex, which is, crazy complex, only to find out when I got to the bookbinder flex and was told, Tara, don't ever talk to your customers about this. We don't ever want to build this. This is so difficult. I'm like, what do you mean? What are you talking about? And here it had been being built for 40 or 50 years. I just didn't know about it. And so I find that that progression happens with many people. And I always kind of joke around and say, no matter where you are in your experience with flex, there's always something new to learn, even if you've been very experienced in working in the high-tech rigid flex area. There's new materials and new processes that are coming out every day. But that's a very normal progression as you learn about these materials. To go back to one of the questions that you asked, the difference between a flexible circuit and a rigid flex. Flexible circuit, as the name implies, is all flexible materials. Rigid flex incorporates layers of circuitry on the rigid pieces. A good way to differentiate it is a flexible circuit can have FR4 stiffeners to stiffen it and have rigid layers associated with it. It's a very common design attribute. A rigid flex, on the other hand, is going to most likely have circuitry on the rigid layers, but it will definitely have a plated through hole connecting the rigid layers to the flexible layers. So that's the primary difference between rigid flex and a flex, straight up flex.
Yeah, that's interesting. So I watched I was kind of a voyeur last night, or actually several days ago, preparing for this interview. I was watching some of your videos on with Altium and others talking about flex circuits, trying to get up to speed, trying to get smart enough to ask you intelligent questions. And I learned of a term you called SWAP, which was an acronym. Tell me what SWAP means.
Space, weight, and packaging, I believe, was the terminology I was using at the time. And that is, one of the great benefits of flexible materials. They're great when you need to reduce the amount of space, reduce the weight. And obviously for packaging, they can be folded over on top of each other. They can be folded around corners. It can, move and be placed around different units in the functional electronics box that's being built. So lots and lots of benefits of flex, but definitely SWAP, or space, weight, and packaging, is one of the primary benefits.
Let's go down that benefit list of rigid flex and flex in general. You talk about SWAP, space, weight, packaging. One of the concerns that would come to mind, particularly these days when we're mounting components to flexible circuits, is heat dissipation. In a traditional rigid board, world, regular laminate world, we put big copper ground planes and we put all sorts of technology in to dissipate the heat. In a flexible circuit, there doesn't seem to be a lot of mass to absorb that heat. How does that work in a flex circuit?
Right. A very thin layer of polyimide is a great dissipator of heat, particularly compared to our typical FR4 rigid materials. So yeah, it's definitely used for heat dissipation and thermal management. So
the material, the polyimide, which I formerly called Mylar incorrectly, the polyimide material is a better heat sink than a traditional FR4 material would be. The actual material itself helps dissipate heat.
Exactly. The thinness of the material, as well as the polyimide attributes. And you were correct probably with Mylar. That is another material that can be used for flex circuits. Oh, good. Okay. One less mistake I've made this year. So tell me about biocompatibility. You talked earlier on a I think an Altium event about biocompatibility as one of the advantages of flex circuits. What is that about? Sure. So polyimide itself is considered a biocompatible material. I think what you might have heard me speaking about is something that's relatively new in the industry, having to do with an additive process. There is now a way to use gold as a conductor instead of copper. So a Veritech has a semi-additive ASAP, Veritech semi-additive process, and you can put gold traces rather than copper traces, which makes the polyimide gold combination, a very biocompatible option for medical devices. One of the videos I saw had you say, choose wisely. And this is probably not fair to you because I'm throwing some of your own words to you completely out of context. But it was on the subject of material selection. So this was part of the communicate your requirements to your supplier. What does that mean, choose wisely? What are some of the concerns, some of the important things when someone is speccing out a flexible circuit or
a rigid flex circuit. What kind of things do the suppliers need to know? And what types of questions should the suppliers ask, and what type of answers should the users provide those suppliers so they get the right material for the right application?
Sure. I think it's probably very important in any printed circuit board design to really consider your materials, but especially important with flexible circuits. There's, and for a number of different reasons. So yeah, when I talk about choosing wisely, there's a few different reasons that I make that comment. I'm often asked for common flex materials. I'm also asked how to help drive cost out of your design. Make sure you're not designing in something that's more expensive than it needs to be. And a lot of that revolves around materials. There are two different types of flex materials. Well, actually, there's many different types of flex materials. But if we're going to look at the more traditional flex circuits and the polyimide and rolled annealed copper laminates, they come in a wide variety of options. You can have anything from 1/2 ounce to 2 ounce copper combined with, anything from 1/2 mil to 5 mil polyimide put together in a laminate for your fabricator. And that laminate, may be bonded together with acrylic adhesive or flame retardant adhesive or be adhesive-less. And that gives a designer so many options, but it's also important that the designer understands what their fabricators are typically building with. For example, if you spec'd out a 1/2 ounce copper on 5 mil polyimide, that could very well end up being a special order if your fabricator is more predominantly using 1/2 ounce copper and 1 mil polyimide or 2 mil polyimide. And if you don't have a particular reason that's driving you to a thickness or an electrical requirement that's going to require that thickness, you may spec in something that's going to be unnecessarily expensive with a longer lead time. Also important to understand adhesive-based and adhesive-less materials. The ribbon cable type flex that you had talked about at the beginning of our conversation, those are often done with acrylic adhesive or a flame retardant version of that. It's a lower cost material than the adhesive-less laminate. But adhesive-less becomes very, very important when you're looking at multi-layer flex. That thickness adds up very quickly, and you certainly don't want to have the flex that didn't flex. I've done that many times. And also it's very
takes away the whole advantage of flex, right? If it doesn't flex.
There's nothing more embarrassing than when you go to supply your customer with a flex that doesn't flex.
Right.
But adhesive-less material is also very important in rigid flex. So we will always recommend adhesive-less material for a rigid flex because you don't want to introduce the acrylic adhesive into the plated through holes with that rigid material. Right. A lot of CTE mismatch issues that go on. So, those are just touching on a couple different things where I say, choose wisely for your material. I mean, it can be performance related, it can be overall thickness related, it could be cost related as well. And, one of the things I always like to say is communicate with your fabricator. And this is a great place to start that. Start with that overall stack up and let them know your requirements and then ask them to help with materials that they use readily, things that are likely to be in stock when you're ready for them. And that'll definitely help, meet your electrical requirements that they've helped calculate in, and then help ensure that you're not adding in extra cost or extra lead time unnecessarily.
Yeah, that makes sense. Not just in speccing out your needs for circuit boards, but for everything. If you don't have a specialty, don't require special items that have to be specially ordered with special lead times and special prices and all that type of stuff. When I look at the movement of flexible circuits, let me put it this way: when I look at the use of flexible circuits, I see one of two types of applications. One where the circuit is bent and twisted for packaging purposes, so they can connect two boards together, and then it never moves after that. And the other is something that has to connect to a device which moves within the product. I think of the old print head things. Back days when we had, even modern printers still have flex circuits on them that move. What is there such a thing as in the metal world, they would call that metal fatigue. You take a piece of metal, you bend it too many times, and it becomes brittle and breaks. Is there a life cycle with the materials that are used and maybe even the thicknesses of copper that are chosen when it comes to being able to actually be flexible and flex throughout the life of the product? Are those concerns? And if so, do they also relate to the in-use climactic environment? Super cold, super hot, lots of thermal excursions. How does all that play into the material selection? And then we can kind of get into tips and tricks for allowing the mobility of these products. It's a very compound question, but
let me give it a shot.
Yeah, thanks.
So all of those things that you mentioned factor into the long-term reliability and flexibility of any design. And, we have designs where they're going to flex millions and millions of times that are designed just for that. We've got flex to install, as you mentioned. And, over time, I have seen the flex to install parts be bent once and something was wrong in the material construction or in the design itself, wasn't as flexible as it needed to be, and that copper cracked almost immediately. And then you have other applications where it can go millions and millions of times and still perform very, very well. IPC does a really good job on bend radius recommendations, which is something that's always really important to take into account. And that is, the ratio of the thickness of the copper to the bend that you're going to have. And then they have specs for, single layer, for double layer, for dynamically flexing. Those are always really, really good guidelines to follow.
Very good. Now, I know in every industry they have their tips and tricks. I produce a tips and tricks series for cleaning once a week, and it's amazing how many tips and tricks we have up here that aren't published anywhere. We just get them over our years of experience. When it comes to fabricating flex circuits, rigid flex circuits, what are some of the tips and tricks that you would recommend to designers in terms of how they spec their part, how they design their part? There's got to be, a David Letterman's top 10 or top 5 type of list. For those young millennials that are on the call, they're probably wondering, who's David Letterman? But, whoever the current popular late night host is today. What are some of the top tips that you can give designers and even users of that material?
Sure. I don't know where to start with that one. So I'm going to start with one that gets left off of the PCB fabrication drawing very frequently. I think we see it often in the assembly drawing, but the assembly drawing doesn't always get passed along to the fabricator who's building the boards. And that is to communicate in that PCB fab drawing how the circuit is going to be flexed and used in end use. Yeah. So, because they're building it in a 2D file and it's being built in a 2D state, not really understanding exactly how it's going to be used, the fabricator is going to have a difficult time helping make recommendations. If they know how it's going to flex and you ask them for advice, do you think this is going to work? What could we do? What are the tips and tricks that we could do to help improve the reliability and flexibility of this? That goes a long way towards the longevity of a flex circuit. But some basic tips and tricks for people getting started is, first of all, make sure you're not over-speccing the material thicknesses, whether that be copper thickness or polyimide thickness. Again, going back to that bend ratio of the angle of the bend versus the material thickness. So thinner materials or adhesiveless materials, a lot of different ways to keep that stacked up as thin as possible. Crosshatch copper, is one thing. I kind of joke tongue in cheek about the flex that didn't flex, but I have had several of those over the course of my career in flex circuits. And it really boils down to that you really don't comprehend how quickly like a solid copper ground plane is going to become rigid. Right, so if you're doing a multi-layer and you have a few of those layers stacked up, before you know it, you can't even, bend the circuit because that copper is solid copper. So in that case, there's a couple different things that you can do. Rather than bond all of the layers together, unbonded layers. So don't put the adhesive between all of the bonded layers. Really significantly improves the flexibility of the overall circuit. and crosshatch copper also, which is kind of a trade-off between electrical and mechanical. So it's things that you have to take into consideration with the design. But even if it's only in the bend radius, adding crosshatch copper in that area, just where it's going to be bending, can make a significant difference in the longevity of that circuit and the number of flexes that it'll be able to use. And another one, going to communicate with your fabricator, is the use of panel plate versus button plate, as we would call it. So, and that you have to know what your fabricator's preferred process is. Some who fabricate flex do button plating or pads only plating as a normal course of action. Some do panel plating. But when you do the panel plating, you're adding in electrodeposited copper on top of that rolled annealed copper. And there are times where changing that and having just the pads have the electrodeposited copper can make a significant difference on the flexibility of a design. You know, thousands of applications have ED copper and panel plated flex circuits. You know, it's a perfectly acceptable fabrication technique that serves well, but occasionally there's going to be designs for a number of other reasons that makes all the difference in the world right there. So something to definitely keep in mind. And then that's a fabrication communication, really. And your fabricator also has the ability to orient the circuit in the grain direction of that rolled annealed copper, which can also improve flexibility. And again, goes back to just communicating with your fabricator so they understand how the things are going to flex in end use and are able to do those little adjustments during the fabrication process.
I heard you talk also about when you specify a mill thickness for the copper. I think the example you gave was 1.4 mil. You correct me if I'm wrong. And then there were applications in fabrication where the fabricator would add up to an extra mil for very specific reasons. So you go from 1.4 mil in your spec to 2.4 mil, which could change things. What are there? Is that a question of just the fabricator being sloppy and adding more, or is there a specific design spec or a feature that requires the fabricator to add more copper thickness because of the way the board was spec'd out? Yeah,
so that goes back to the panel plate versus the button plate that I had mentioned. So to make that plated through-hole connection between layers, fabricator is typically going to plate, anywhere between 0.5 mil or 0.7 to 1.4 mils, I should say. So 1/2 ounce to 1 ounce copper in that hole to make that connection. And that's standard process. The difference is in a panel plate, that copper thickness, maybe that 1.4 mils of copper, is going to go across the entire panel and become part of flexible circuit trace. If you use just pads only plating, you will only plate that copper in the pads in the plated through hole, which leaves the rest of the panel as the rolled annealed and more flexible copper.
Yeah, very interesting. So as IoT makes its way into our lives, Internet of Things, and specifically wearables, textiles, things like that, is that a traditional use or is that a use of traditional flex circuits, or are electronics and textiles an entirely different animal?
No, IoT is a great use for flex circuits. Just by nature, a lot of that is going to be small, needs to be lightweight, maybe embedded into something else, maybe have to wrap around it, another piece as it's gathering data, things like that. So blends perfectly with flexible circuit materials that are thinner, lighter weight, more flexible. And the other thing that we haven't really talked about is shape. Some of these IoT configurations, wearables, things like that, it's very beneficial to have a non-traditional shape. Our circuit boards are square or rectangle, occasionally round, but flex, you have all the creativity in the world to how you want that piece to be shaped in its end use. And so I think there's a lot of advantages there for IoT.
Yeah, you're not stuck with a standard Eurocard specification of a rectangular or square board.
Yeah.
I think of, my audience is probably tired of hearing this, but whenever I talk about IoT, I kind of give the example of of stupid IoT, which is electronic connected toothbrushes. That's just an example of us putting electronics in things just because we can, not really because anyone's asking us to. But that's a good example of a non-traditional board because the form factor is already there. And because these are form factors, packaging sizes that were historically not embedded with electronics, the form factor is not going to change. The electronics have to change to fit into that form factor. So yeah, you're right. That is a pretty good use of flex circuits, particularly in a lot of these IoT devices. They're not necessarily extremely sophisticated. So we don't really need 24-layer rigid boards, all stacked up with tons of bottom terminated components on it. A lot of the uses of IoT are relatively simple devices that have already been miniaturized and can go into a very small footprint. What types of challenges does IoT place on circuit boards in general? And I'm thinking kind of down the line of harsh environment. We tend to, if electronics go with us, we tend to go into nasty places where it's hot and cold and humid and maybe subject them to shock and vibration and things like that. Is that a concern any higher or lower when it comes to flexible circuits, or is it the same for any kind of circuit assembly?
I don't have any data to answer that question with. But, the thought that comes to mind is it's still important to consider, no matter if it's a flex design or a rigid design. But I do think that flexible circuits, just by their nature, are able to absorb a lot of that shock and temperature and things like that just a little bit better.
Like, yeah. Just
they're
they
thinner,
move.
they're more flexible. It gives you a little.
Sure.
I think it maybe opens up that window a little bit for you.
Yeah. Can any type of component be soldered to a flexible circuit, or are they limited to, more traditional, simple components? And I'm thinking in the world of bottom terminated components, QFNs and things like that. Are those mounted to flexible circuits, or do they, or does that technology require multiple layers and a more rigid substrate to be mounted to?
Well, the minute I say you can put any component on a flex, there'll be somebody to correct me.
Right.
But in general, yes, I do think that you can put nearly any component that you would want to put on a rigid board, you could put on a flex board, with the caveat that you need to design for that. Having a piece of FR4 supporting that flex. So your heavy connector isn't putting all of the strain on a very lightweight flex, which is going to crack your conductors very quickly.
Right.
So as long as there's some type of rigidized material to help support that component, I think you could probably use pretty much anything with a flex, as long as you're able to accommodate that support in the design.
Before we move on to our next subject, is there any advice from the trenches, all your years of experience in supplying these flexible circuits and other more traditional materials to your customers? What are the common mistakes people make? Do you have any examples of common mistakes people make, and some tips and tricks for avoiding those mistakes? Is there a poster child? I know from my industry, there's one or two that just happen all the time, and I'm sure you see that in your industry as well. Can you share any of that kind of parting advice for this subject on flex circuits and rigid flex?
Sure. The first thing that comes to mind probably isn't specific to flex, but it is the mistake that I see happen over and over and over again. And that is the fab notes. You can spend 400 hours working on a design that's so complex, I can't even fathom how a designer, gets to the final version of that circuit board. But at the same time, if those fab notes aren't perfectly clear, or if a note got copied over incorrectly or got left off of the drawing for whatever reason, that stops everything at the fabricator. And usually, when you're going out for your prototypes, there's time constraints, and the last thing you want to do is hear that your job is on hold And I would say still today, 80 to 90% of the PCB drawings, whether those be flex, or rigid boards, are actually stopped at front-end engineering just to clarify print notes and ask questions. So maybe the drill chart doesn't match the data perfectly, or the size doesn't quite match perfectly. You know, just something got adjusted and didn't quite get finished. So I'd say that was probably the number one reason that jobs go on hold and progress stops. It's just with those fab notes. And I think in terms of flex specifically, the problem that I see people have most often is actually in the simple flexes that you had talked about, and making sure that there's enough rigidity behind the components that are going to be used, because that will very easily crack your copper if your components are too heavy for the circuit once it starts flexing. And just not understanding that, you know, there's something with flex, but once you get it in your hands and feel it, it can be more flexible than you expected. Maybe it's going to be more rigid or stiff than you expected. So those are all things that factor into the design and overall experience with flex.
Your experience with the fabricators, you were a broker mainly, is that correct?
Yeah, my company that I actually just moved on from, Omni PCB, is a manufacturer's rep group. So we represent PCB fabricators. They have different specialties. So my background has always been fabrication.
Right. So these fabricators, will they look at a print sometimes and just go, no, and reach out to their customer and recommend changes? Or is it a case where it's on the print and they go, okay, that's what they want, that's what they get? Or is there a little bit of both?
I think there's a little bit of both. And I think that depends on the fabricator that you're working with and the relationship that you have. It's funny, I just did a series, it was Ask Tara, and people were sending in questions. And one of them is, why doesn't my fabricator tell me when I'm doing something that's poor practice, you know, for design? And I'm like, I don't know, from the fabrication side, I feel like we do do that. But I think that just shows that maybe that communication isn't as good as we all think it is. I think some fabricators are very fast to jump in and say, hey, I think you could do this, this, and this to improve the design. And maybe by improve the design, they mean make it more manufacturable. The yield's higher, the reliability is greater, ultimately the cost is down, you know, and make these suggestions. That's often my experience. But I also think that there are fabricators as well that you send in a drawing, they're going to do their best to build whatever's on that drawing for you, whether that be good design practice or bad.
Right. Yeah, you always worry about getting what you ask for.
Yeah, exactly. But it goes back to my soapbox that I'm always on. I feel like, particularly with flex, is just that open communication with your fabricators. You know, most fabricators have field applications engineers or front-end engineers that, you know, that's what they love to do every day, is talk to customers, make recommendations, help make, you know, designs more manufacturable. And they're building these every day, all day long, seeing everything. So that's just a wealth of knowledge to take advantage of, especially if you're new to flex, and even if you're not.
Right. No, that's a very good point. Let's switch gears here for a moment and talk about a technology that in my world is just a little bit of a mystery. So you can help me bring this up to speed. You co-hosted or co-presented an additive exchange with SMTA not too long ago. Am I right on that?
Yeah, with the Additive Electronics Tech Exchange, it was our second year. Co-chaired that with Lenora Clark. Okay,
good. Then I've got the right person. Tell me what additive manufacturing is as it applies to our industry.
So, you know, that was one of the things that Lenora and I identified right away when we started talking about this and planning our first year event, was when we say additive, I think we were talking additive conference was the terminology we were using at that time. And immediately, you know, we got hit with 3D printing and printed electronics and things like that. But what Lenora and I focus on in the conference that we've been co-chairing is we now term it additive electronics instead of additive manufacturing, which helps narrow that definition down to circuitry. And then the event that we host is actually narrowed down even further. So what we're talking about in those events is additive electronics, and specifically how it relates to that gap kind of between PCB scale and IC scale. So 3 mil line in space down to 5 micron line in space. And what technologies are filling that gap? And what do we see coming on the horizon for that?
So help me understand exactly what that process is. Are we printing? What are we printing, if we're printing anything? And my understanding of additive manufacturing is it's, again, it's used for a lot of different applications and different industries, and all has a slightly different connotation. But in our world, what exactly are we printing? What are we adding through this additive process?
Okay, so I will explain a Veritech semi-additive process, or ASAP, which is commercially available right now in 3 printed circuit board facilities here in the US. So in that case, let me think, where do I want to start? Okay, so when you're starting with typical printed circuit board manufacturing, whether that be rigid or flex, it could be either one. You start with a laminate that your fabricator purchases. And then they ultimately etch away the copper that they do not want, creating the circuit pattern. So the additive process is going to do that in reverse. It's going to start with the laminate and then etch away all of the copper on that piece of laminate, leaving your bare dielectric, and then add back the copper that you need for that circuit pattern. It'll start with a very thin layer of electroless copper, much thinner than what we're used to with traditional electroless copper plating. And then it will be, photoresist, image, electrolytic copper plating, all the same processes that we're using in subtractive etch circuitry today. The primary difference being, as I said, you're starting with a bare dielectric and adding copper to that. And because you're doing that, you can have much finer feature sizes than we see being limited at the subtractive etch process. For example, subtractive etch is usually limited around 75 micron trace in space or 3 mil line in space. Some can go down to 50, but that's only a handful. That's not the bulk of the fabricators in the industry. And the additive process can go down to 15 micron or 25 micron, so wow. Sub 1 mil line in space, or anything in that gap, between 3 mil and down. And, we're finding some great RF benefits to that as well, because when you're etching that very thin layer of electroless copper, it's a flash etch. It goes very quickly. It doesn't degrade the trace. With subtractive etch, we see that trapezoidal effect. So that's eliminated. The traces are now straight up and down, which has RF benefits as well.
Yeah. So we can get more traces into a smaller footprint, so to speak, much finer traces with additive processes than we can with traditional processes. When I think of that type of process, in my head anyway, logically, it seems very slow. It seems like a much slower process than traditional fabrication. Is that correct? Is it like any printing process, a very specific, very accurate, and very slow production method?
No, actually not at all. It is going through the exact same electroless copper bath that's currently being used in subtractive etch, the same electrolytic bath. There is a chemistry that's applied to it, a liquid metal ink chemistry. So that does take a little bit of extra time to apply that chemistry, but it's just a pretty standard chemical process and timing of that and curing. And then you also eliminate some of the electroless copper steps as well. So really, sure. It's not, it doesn't take, any significantly longer period of time, and it follows most traditional printed circuit board processes.
Okay, well, thanks for straightening me out there. I thought it was a much slower process. So what are the advantages and disadvantages? I would think if it was all advantages, everyone would be building boards that way. So what constitutes a good use of that technology? What constitutes an avoidance of that technology? What's the deciding factor? Sure.
Well, so to address the advantages first, because I do think that this is going to be a game changer for PCB design, right? All of a sudden, well, not all of a sudden, our PCB designers today and for many years have been challenged with, us consumers wanting it faster, it lighter, more functionality in smaller spaces. And ultimately, we're hitting this crunch time in printed circuit board design, where with the 75 micron or 3 mil line in space, you just can't route out the devices that you need in the space that you have. And so you're going to multiple lamination cycles, multiple levels of stacked or staggered microvias, all increasing time, increasing cost, decreasing reliability. And that's the world that we live in with subtractive etch. All of a sudden, this designer has the ability to use, say, 25 micron or 1 mil line in space. It changes the way that you look at designs. And I think we're just scratching the surface. This is relatively new technology, so scratching the surface on how to best apply that. I've seen some cases. I have one example where we're working on a 12-layer design. It was 12 layers and it was 3 lamination cycles. They went down to 8 layers, used 4 of them with additive and 4 of them with subtractive etch, combined those 8 layers, and then reduced it from 12 layers to 8, but probably more importantly, from 3 lamination cycles to 1. So that's a great use. The cost went down. It was much simpler to build. And when I say reset the technology curve, that's kind of what I mean. Like, we're able to accomplish the same thing in a much simpler way with this ability for 25 micron trace in space. But yeah, I'm working on a series now with designers. I'm doing short little videos trying to figure out how creative can we get in applying this, because just applying it to an already complex design is probably not the greatest benefit of the technology. You kind of say throw in the kitchen sink, everything but the kitchen sink. So if you take something that's already crazy and add in just smaller traces, I don't think we're really getting the huge benefit that we could get from just simplifying overall. And to address your question about the disadvantage, I think the disadvantages right now are just that. We don't know the best way to apply it. We haven't developed best practices. So a lot of it's collaborative and learning as we go, which is really exciting, but it's also difficult for people, especially designers. PCB designers are used to having, here's my design rules. Here's what I need to do. How do I get from A to B, right? And there isn't that yet. So we're all kind of working together trying to get through that learning curve of how to best apply it.
Do you think that's going to be a generational thing? Do you think, some of the old timers, like my age and up, will resist that technology, and some of the younger designers will embrace that technology? Or do you think that really doesn't apply from an age and experience standpoint, that it's new technology is new technology?
I think it'll be both. I definitely think it'll be an easier technology for younger, newer designers. I should say newer, not necessarily younger, right? People that don't have all the years of experience designing one way, to just adopt it, right? Here's what it is. Oh, let me see how I can work with this. This is great. But I also work in the series I'm doing. I've got a bunch of very well-seasoned designers who are so excited for the ability. One of the people I was working with said designers are always out shopping, he called it, which I thought was a good analogy. Out shopping because they're always, trying to balance all these different requirements for any type of electronics design, and how can they, what's out there available to help make that a little bit easier, ways to solve problems. So he said we go shopping. So now he's shopping and he's seeing 25 micron, line in space, and the light bulbs go off, and he's like, oh, we can do this. This is going to be so exciting. And I had somebody else contact me. It was one morning, thought of it in his sleep, I think. He was like, look what we can do. And he took something that normally was taking him 6 or 8 layers, with blind vias to route out, and he routed it out into a double-sided board just by changing the line within space. And again, two, very experienced PCB designers being very excited about it. But yeah, I do think in general, there will be people that are hesitating, and there's going to be people that jump in with both feet.
And I do like your slight shift from age to experience. I think that's a better way to put it, because it really doesn't have much to do with age. It has much more to do with experience, which sometimes brings in age. But there are some people who get more experience over a shorter period of time too. I mean, so it's relative that way. Mm-hmm. So get out your crystal ball, and what are your predictions for our industry over the next several years, 5 to 10 years. Do you see us moving in a specific direction? Things that come to mind are the electrification of cars, the miniaturization of assemblies, the proliferation of IoT. That's what I see when I look out there. Mm-hmm. Do you see that as well? And do you see opportunities and challenges coming our way that with any degree of specificity?
Oh, it's my great crystal ball.
Yes.
I see all the same things.
We're going to play this back 10 years from now. Yeah. We're going to play it back 10 years from now and see if the psychic Tara Dunn was accurate.
See if we were right. No, I see all the same things that you do. I see that overall the miniaturization is going to continue, and we're going to have to learn how to deal with that from an electronic standpoint. And that's why I think I'm so excited about the additive options that are available, because they're opening up a whole new world. And I talked today about the ASAP process. There are multiple generations of that type of technology currently in development. So as we kind of move through the learning curve with ASAP, we're going to be ready for the next, which is maybe embedded electronics in a way that's new and not something that we're doing today. I think, in the automotive world, there's a lot of applications with sensors and things like that. And I think that number is just going to continue to grow as well. And, I think some of these additive processes that we're looking at, particularly the ASAP, the enabling piece of that technology is not limited to 2 dimensions. So it can also be applied in a 3-dimensional way. And I see that in development on the horizon as well.
So we'll never run out of things to do. We'll never run out of problems to solve.
We'll never get bored.
We'll never get bored. That's for sure. That's for sure. So Tara, I saved the most important question to the very end. You were the producer of an event within our industry with the most awesome name any event in our industry could have. Keep in mind, sometimes from the outside world looking in, we're not the most exciting industry to be in. But you had an event called Geek-a-Palooza. Mm-hmm. I know right now everything's, the hold button's pushed, the pause button's pushed right now. Nothing's happening right now because we can't get together. And it's probably hard to do an event like that through cameras and screens. But tell me what Geek-a-Palooza is and the history of it. What made you think of that? Was it too much to drink one night and it just got in your head, or because that's an awesome name for an event?
There's probably some truth in that statement. No, so Tanya Martin, now heading up SMTA, her and I have been friends for a long time. When I first met her, she was working for a contract manufacturer. And I, of course, was working on the fabrication side of things. And so we would get together and, do lunches, brainstorm, things like that. We actually did. We joke about it now, but we would make our own contests, right? How many cold calls can you do? And it was just our thing. We had fun with it. And we were talking one day over lunch and kind of talking about the fact that in our local area in Minneapolis, at the time, there wasn't a lot of in-person events to go attend. Maybe a small one here or a small one there, but nothing that was all encompassing. 10, 15 years earlier, there had been much larger group meetings for networking and things like that. So kind of were complaining about it and turned that all the way around to, well, why don't we do something about it? And so we decided to host an event and see how many people would be interested in coming to it. And did come up with the name Geek-a-Palooza. I think that was Tanya Martin. I owe her that credit for that. And we started planning it, and we were going to do it kind of in the, back room at a local, restaurant bar, thinking we would have, 30 people if we were lucky that wanted to come to this. And we had, I forget the number right now over the top of my head, but we were well over 100 people. We ended up, and wow. I think we were close to 150. We ended up having to scrap that idea and rent out a much bigger space. And it really turned out to be a really fun event. So the idea behind the event is networking, obviously, but it's a very social event where there's not like trade show booths and things like that you go visit. There may be sponsored tables, but it's very laid back and you can come and go, as you want. Music, food, cocktails, games. And I think more importantly is the fact that we are inclusive of the entire industry. really recognize that it takes all aspects of the industry working together to create, a successful electronics device. So inviting, materials and design, fabrication, assembly, manufacturers reps, the components, the associations, really inviting everybody into one spot for just a few hours of fun to kind of talk and, get to relate to each other on a way that's, not through the screen or behind the screen, depending how you look at that. So we had a great time with it. We hosted it several years here in Minneapolis, and we also did an event in California, and we did one in Boston as well. And I really hope that at some point in time, we're going to be able to continue that, because it really was a fun thing to do.
Yeah, for sure. I increasingly miss the physical events, and I never have gone to a Geek-a-Palooza, so that is now on my bucket list, on my career bucket list, to attend one of those events. And I think it's an important event in that our industry is quite siloed. The board fab industry and the assembly industry are right next to each other, along the riverbed. We're just downstream from them, but we know very little about that industry. It seems like it's, this black art, somehow, somewhere in some other country, something is made, or even here, and then it's shipped to us, and then we open it up, and there's just, from an assembler standpoint, there's just not a lot of appreciation for the technology and the effort behind building a board, a bare board, and there's just not a lot of knowledge. At least that's been my experience, and I'm not sure if that applies the other way around too. There just seems to be this great wall separating industries that are just right next to each other in terms of producing a product. So to get the board fab industry, the designers, the assemblers, all facets of one industry together, I think is a good move. It helps break down some of those silos, and I think it helps the assembly side understand the fab side, and the fab side understand the assembly side. Does that ring true in your world as well?
Oh, it absolutely does. And I have a great example. I think it was the Orange County event that we did Geek-a-Palooza at. I remember just walking through the room and happened to notice a conversation. I walked up, and it was an assembler and a fabricator, and they were talking about a problem that they were having with a particular design. And they started talking about materials, and they went, wait a second, he's right over here. And they pulled him in, and here, they had a 10-minute conversation and made so much progress towards solving, that challenge that they were having right there with, a cocktail in their hand, listening to music. But it does help break down the barriers, and to see people face to face and interact that way. I remember years ago, before the internet, I don't want to admit that I worked in the industry before the internet, but I did. There was, maybe at the time, 3,000 fabricators or something like that in the United States. And it was pretty common for assemblers or designers to go visit fabricators, and fabricators to visit their, assembly in back and forth, and really got a much better opportunity to learn about the challenges that each side faces. And I just don't think we're able to do that as well today. For one thing, there's maybe a tenth of those printed circuit board fabricators left in the United States. So just the travel and the proximity is a challenge in itself. And I think with the internet, it seems like all that information should be available to us readily. Go out and search it on Google or whatever your choice of browser is. And but you lose something in that. And as quickly as you can get that information, you do lose the human element of that and what challenges people face. So I really like any event that's going to help bring people together to communicate more face to face.
Yeah, well, I'm looking forward to the restoration of those events as well. You can only spend so long looking into a camera, and a screen.
I've been a lifelong traveler. Like, I've probably traveled half of every year for my entire career, and I haven't traveled since March.
Right. Well, I did my first business trip a few months ago to Minnesota, to SMTA headquarters for some new board member orientation, and it just felt so good to sit on an airplane. This, which was normally just not the best experience in the world. When you're a road warrior, it's just a means to an end. I felt very special to sit on this airplane and and be given my little 4-ounce bottle of water served in a Ziploc bag for my safety, and all the bizarre things that they're doing right now. But it did feel good. It felt very normal. It was a great sense of normalcy for that one moment.
Yes. I look forward to doing that again, and I'm promising myself I won't complain like I used to about the travel.
Right. Exactly. I asked for a drink, and they said, well, my only choices are beer, wine, and water. And I'm like, I just want a soda. And they said, no, beer, wine, and water. But I didn't complain. Any other time, I would have been, writing a letter to the president of the airline. But no, not now. No. And everyone, all the crew, just exhibited this vibe of gratefulness that we were traveling on their airline, and everyone appreciated each other. It was a whole different experience. It reminded me a little bit of immediately after 9/11, where everyone kind of pulled together and we're all in the same boat, and the differences were put aside, at least temporarily. And this felt kind of the same way. We were a group of warriors in the middle of a pandemic and this silver tube flying through the sky. Mm-hmm. We all had a common bond for a moment. But I'm sure 3 weeks after this thing is over, it'll all be, everyone bitching and moaning about, airline fees and something being 6 minutes late and, all that stuff. Yeah. The overhead bags, bins being full. We'll get back to normal, I'm sure.
I have to retrain myself.
Right. Exactly. Well, Tara, thank you so much for agreeing to be my guest today. And I really appreciate all of your knowledge, specifically in the flex and rigid flex world and board fabrication in general and additive manufacturing. Thanks for bringing me up to speed on all of that and my audience as well. For anyone who wants to get a hold of Tara, I will have her contact information in the show notes. If you're listening to this through Google Podcasts or Apple Podcasts or Spotify, you don't see those show notes. But if you go to Spreaker.com, Spreaker.com, that's the host site for this podcast. And in there, you'll be able to see the show notes. And within the show notes, we'll have Tara's contact information. So again, Tara, thank you so much for agreeing to be my guest today. It's nice to see you. I'll look forward to seeing you in a more face-to-face environment at the next Geek-a-Palooza.
Yes, absolutely.
Or whatever event it is.
Thank you for having me. This was fun. I enjoyed it.
Yeah, it was for me too, and informative. So thanks again. Take care.
Thank you.
Well, that's another episode. Thanks for listening to the Reliability Matters podcast. We release new episodes on the second and fourth Tuesday of each month. Don't miss an episode. Subscribe to Reliability Matters on Spreaker.com, Apple Podcasts, Google Podcasts, Spotify, and virtually wherever you get your podcasts. A special thanks to Circuit Assembly Magazine's PCB Chat, who syndicates this show at PCBchat.com, where you can also listen to Editor-in-Chief Mike Buto's interesting discussions with industry leaders. You can also listen to the show at Ascendo Reliability at reliability.fm. This show and many other reliability-based podcasts are available there. Thanks again for listening. We'll be back soon with another episode of Reliability Matters. In the meantime, stay safe, stay healthy, stay happy, and keep doing it right.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.